The next talk is with Kaleb Dempsey of Racing Service Testing Laboratory and Rainier Sensing. And Kaleb is going to talk to us about transitions of thermal temperature in wax to supplement previous discussion about synthetic surfaces. It's going to be virtual, so Kaleb.
Well, good morning, everybody. My name is Kaleb Dempsey, and today I will briefly be talking to you about, temperatures on the synthetic racetracks and kind of what we know about them, how do we test for them, and some other considerations that we can, look at as we move forward with synthetic racetracks. So, as mentioned, there's been a general increase in synthetic racetracks. We now have Gulfstream Park, Santa Anita, and Belmont moving forward with, installation of synthetic racetracks. Unfortunately, we have lost Golden Gate and Arlington Park, but the key feature of the synthetic racetracks is that they are coined an all-weather surface. That is, that they have this vertical drainage. And what makes that possible is that we have this wax coating or a polymer coating on the sand fibers and potentially the rubber particulates that are in the surface. And that's what makes it, allows that vertical drainage. It provides this hydrophobic nature for that. It repels the water. It lets it shoot straight through the material towards the bottom, towards the drainage and out off the track, unlike a dirt track, which would be draining horizontally, as we all know. Statistically speaking, we know that the synthetic racetracks have been, relatively safer compared to dirt and turf surfaces, measured by the injuries per 1,000 starts. Over the past decade and a half, we have actually grown to, get a better understanding of what's going on with these synthetic racetracks. We can now fully characterize, or at least nearly fully characterize, the material. So what does that mean? Well, we can actually test the components of the synthetic racetracks. We can come out, we can grab samples, we can actually break it back down into its constituents, and we can test. So we can test the sand, we can test the fibers, we can test the rubber particulates, but perhaps most importantly, we can test the wax. Now, why are synthetic racetracks safer? We're still working on understanding what that link is. There's a need for more research. Why is it safer? Is it because, we're no longer having to deal with moisture? Or could it be the mechanics of the surface, when the hoof is coming down and striking the surface? Is it potentially showing any difference compared to what a dirt or turf track would be? And we're still working on trying to answer that question. But first, we always have to start with, well, what is going on with the synthetics? What is the synthetic material made out of? And that's why we've developed and published test methods. There are, of course, as we have talked about, there are some criticisms of it. We know that drainage can be a potential issue. Some of the things that I've heard over time is that, material balls up in the hoof. Anecdotal, we don't have, particularly any major evidence to support that. I've also heard, from people saying that, there's more soft tissue injuries compared to dirt or turf. Again, that's anecdotal. We don't have any epidemiological data that's actually supporting that there are more soft tissue issues, or at least not to my knowledge. There's also the environmental and health concerns. We are sticking petroleum-based products into, on the ground. There's, when it rains, when it drains, some of that, the chemicals that could be in the track, the fiber, there is the potential for the environmental concerns on that. And then, we just discussed the temperature differences, and we know that there's been actually considered what we would call, a morning track versus an afternoon track. And we actually do have evidence that supports that. And one of the biggest criticisms too that I've heard is obviously the costs of installation, transitioning from dirt to synthetic, as opposed to just putting in another dirt track. The costs are significantly different. So we'll briefly talk about, I'm going to move through this relatively quickly since we kind of already know what is in the synthetic, but for those that don't know, One of the reasons that, of course, we like synthetics is the drainage factor. But we also are substituting the clay content that we would find in the dirt and the turf with the wax or the polymer coating. And that's one of the big differences there is, okay, we're still having a binding material, but it's going to be different. We're achieving that with the wax. And I discussed earlier that we have the sand, the fiber, and the rubber particulate. One of the most important features of a synthetic track is the sand content. We're looking for high quartz content. We can test to see if the racetrack has the high quartz content. We're looking that there's going to be low phyllosilicates. That's going to be your clay content. And we only want to see trace amounts of other types of minerals. And we're looking at the hardness of these minerals. So quartz as opposed to feldspar. It is going to be a narrow particle size distribution. That means you're going to have a lot of sand of the same size. And we can test these methods through X-ray diffraction. That's how we know the quartz content. Of course, we do particle size distribution, so we know how big the sand is. And then we look at the microscopy so we can make sure that it's not going to be too angular or too rounded. Fiber content, it varies quite dramatically from track to track, but we are able to test and identify what fiber is being used. We see a lot of polypropylene. We see a lot of like the elastic, the spandex, maybe polyester, the nylons. Generally, these strands, the fiber lengths are going to be about 3/4 of an inch to 1.25 inches. And we're going to see about 4% or less of the total fiber content present in a synthetic racetrack. Again, we can all test like this. I have seen, with the newer Tapeta 10 that the fiber lengths are generally a lot more variable and they tend to have a tendency to clump up. In some cases, it can even be mat-like. But we can still, again, we can test for these. We can figure out what they are and how much of the fiber content is present in the surface. The rubber particulate, here is a good example of what made the poly tracks, or at least like the older tracks, black. A lot of it was because they had this crumb rubber in there, and it has a material called carbon black, and that stuff leaches out, and that's kind of what turned the tracks black over time. But we still see that it's common to add in the we call it like the jelly cable, and these are like the like when you strip an electrical wire, it'll be like that type of material that makes it in. And again, this is something that we can test for and identify what's present in the material. And the wax, which is what we're going to be mostly discussing for the rest of this presentation. We know that it's petroleum derived, specifically that it's a paraffin-based wax. So, you can kind of think of it like, your candles, so to speak. And these waxes are fairly complex, but we see roughly, we can measure the total wax content present in the surfaces. We see about, with the newer tracks, I believe we're looking at generally less than 5%, but I have seen about 8% wax content on some of the race tracks. And these waxes have a large temperature ranges, particularly, they have a higher melting point, but they can have different physical properties, which we're going to be talking about right after this. And we can actually strip these materials from the racetrack. We're able to extract the wax and then run it through a series of tests so we can actually understand how is a wax going to affect a synthetic racetrack across a temperature range. So before we get into that, I want to kind of, talk about the wax in a little more simplistic term. Normally, when we think of wax, we probably think of it like candles, like I mentioned before, but I want us to consider wax maybe not as like a candle, but consider it like little fibers that we have shown here. And what do we know about fibers? They can vary in length. They can be short, they can be small. Fibers, they do break down over time. You come in through with a power harrow, for example, or just any harrow, that's going to break down the fibers over time. Well, we still see the same type of thing happening that we do with wax, is that, you leave the fiber out in the sun and it will become brittle through, heat degradation, the UV degradation coming from the sun, off gassing, and this is like the same type of deal. That's what's causing like the plastic in your car, like the older cars, they could become really brittle and they break. We're talking about the same type of mechanisms here. We know that some fibers are going to be stronger than others. Some won't break down. Some might, be better at entrapping things. I'm talking like a microfiber towel versus, like an old cotton rag that you'd use for cleaning up some oil. And we have like these different layers of entanglement. And so how is the wax like the fibers? Well, just like the fibers, they're both chains. They both waxes like fibers are varied in length. They can become entangled like fibers, and they even break down like the fibers. And so now I want us to think of wax like a paste, like it actually is, but we're talking about a paste of these tiny long fibers. And we can actually look at these fiber lengths through a method called gas chromatography. And so we can actually see if, we're having these short fibers or these long fibers, or these short chains or these long chains. And waxes in general, we have shown that some tracks are going to have, mostly long chains. Some tracks are going to have mostly short chains, or some tracks are going to have short and long trains. And so the figures here on the left, we have Woodbine from 2011. You can see here that, we have these two like kind of peaks. The left-hand side will be your shorter chains or your shorter fibers. And the right-hand side, you have these longer chains or these longer fibers. And the figure below that, we have Hollywood Park back in 2011. And you can see that it actually, compared to Woodbine in 2011, it didn't really have any of the shorter chains compared to Woodbine. It was mostly just the long chains. And these chains have different properties, and these chains are mostly what's going to be affecting, some of these thermal properties that we're going to be talking about. Will it work better in the cold versus the heat, or the morning versus the afternoon? We're going to have different melting points as a result of these fiber lengths or these chain lengths. And we're actually going to be having multiple melting points. It's not just going to be one. I mean, generally, when we're talking about the melting point of the wax, it's the melting point on which all of the wax melts, not just like, the short chains versus the long ones. It's all of them. And so when these all come together, it creates this paste-like material. And depending on the temperature, we're going to see that the wax acts more like an oil. It's going to flow, or it's going to be a candle. It's going to be like stiff and rigid. And a lot of this is going to be dependent on those fiber or chain lengths and the temperature. So with that information in mind, let's take a look at a practical example. So here, what we're looking at is a study that was done back in 2010. And we're looking on the left-hand curve. This is the temperature of the racetrack at Del Mar in August over a 30-day period. So this is just a quick snapshot from like the 16th to the 20th. And the blue line right here is the surface temperature, slightly into the pushed right into the ground, with the green line being the air temperature. And we can see that as air temperature increases, this temperature of the synthetic track increases. No surprise there. And of course, it decreases with the decreased air temperature as it cools off. And one of the findings was that as the temperature of the track warms up, we were actually seeing a change in the race and work times of the horses. So the track gets hot, the track gets a little bit slower, gets a little bit deeper. And that maybe not be too much of a surprise for everybody, because that was one of the complaints, is we were saying, oh, a morning track versus an afternoon track. And of course, you're like, yeah, the wax melts as it gets hotter. So why was that surprising? And, the question that I actually am more interested in is, could that have been prevented? Could the track have been designed in such a way where you could have reduced the effect of surface temperature on your work times by selecting a material that would be less effective or less sensitive to the temperature. And we're able to kind of look at some of these thermal properties and make these decisions on a test called DSC. The DSC is actually what kind of brought me into horse racing. I started doing a bunch of DSC work on the synthetic racetracks in 2014. And ever since then, I've, started going track to track, doing the testing. So this is kind of what roped me into the industry myself. So what is DSC? It stands for differential scanning calorimetry. Say that 10 times fast. This is a method that we are able to use to determine the thermal properties of the material. And there's a lot of scientific mumbo jumbo in here. But the key points that we're able to learn from this is that we're able to put heat into the wax, and we're able to measure how much heat that we are putting into the wax to make it increase in temperature. And this is actually how you determine what the melting point of the wax is. You use a method like DSC, and this is where you can definitively say that this is where the temperature at which the wax melts. But we also learned two other important variables called the glass transition temperature. This is going to be the temperature in which we start seeing the wax act less like a paste or a solid and more like a liquid. And there's this degree of crystallinity or enthalpy, and I will touch back on that here shortly. But for now, I just want us to focus on the melting point and the glass transition temperatures. So what am I really talking about? Maybe you guys, some of you are familiar with welding, welding aluminum versus steel. You see that the aluminum, it's relatively more difficult to weld than steel without a lot of practice. And part of the reason is that it takes less energy to heat it up and it's faster to cool down. So aluminum, you can heat it up really quickly and it'll cool down really quickly. If you were to do the same thing to the steel, you'd see that the steel would heat up more slowly, and then of course it would cool down more slowly. So there's like this window when you're talking about welding and the workability where you would potentially burn through the aluminum if you were doing the same type of method that you were doing on steel. Another way to think of this is motor oil. As I'm sure a lot of us are familiar with motor oil, we have different weights, or we call them weights, but it's really, we're talking about like these different winter grades. So if you're running your tractor in more freezing conditions, you're probably going to have a different type of oil that you would, as opposed to if you're running it in hotter conditions. And what you're trading off here is the viscosity of the oil. How is the oil likely to flow depending on the temperature that you're operating in? And waxes are not that much different. We should be looking at waxes and selecting waxes based on these operating temperatures. And the DSC lets us measure these properties and determine what kind of temperatures we have here. So, looking at this curve here, we can clearly see where the melting points are. And through a quick calculation, we can even determine where these temperatures are for the glass transition. And I want you to take a notice here that we actually have two melting points for both. This was Turfway Park in 2017, and this was Windstar from 2018 before they switched back to dirt themselves. And you can actually see that we have two peaks here. That means we have two melting points of this wax. And what we're actually looking at is that we're seeing two melting points of one of the short chain fibers. And then we're seeing another melting point of those longer chain fibers. And these characteristics are what's really going to give some of these tracks their performance in colder versus hotter conditions. So what am I really talking about here? Well, if we're taking a look at the thermal properties for both Windstar and the old Turfway Park track, if we could actually change the temperature at which it starts acting like a solid versus a paste, or if we could actually move the melting points of these waxes, we can actually tailor these materials for whether, you're going to be working for, a more colder conditions like turfway or potentially woodbine towards the end of the meet, or maybe we can move it to the right. So it's going to be better for tracks like, Santa Anita, where the temperatures are going to be a lot higher here. So, as we increase temperature, we know that the wax tends to act more like a liquid. It coats, it gets a little sticky. But if we decrease it, it starts to become more solid. It'll start balling up. It was mentioned earlier that, anywhere, around 8 degrees Celsius, or, getting around freezing, we can start seeing the material separate out, and you continue to decrease it, the material falls, decrease the temperature, material tends to fall apart. But we see the same being true as you increase the temperature. We start losing some of the binding ability of this wax, and as the result, the temperature changes. So this is perhaps a very simplistic way of looking at the DSC data and what it could potentially mean for when you're doing a wax selection. And so here I kind of have like two lines dropped into green. This is where the wax is really going to act like a paste. It's going to be really good at coating. It's going to be really good at binding. In the yellow regions, we're going to have it act either more like a solid paste. It's still going to coat. You're still going to have good binding. Or you're going to act like a liquid paste. We're getting hotter, so we are actually have some of the wax already partially melted. It's still going to coat and it's still going to bind. But if we exceed the melting points of both the wax, it's going to be liquid. It's still going to coat, but it's going to have relatively more binding. But on the other side of the coin, as we start getting more solid, you might see that as you work the track, it starts actually separating out. This is where they were talking about like the fibers and the sand separating out and coming up to the top. And you're going to get relatively poor binding. So again, this is just a very subjective and imprecise way of discussing and looking at the wax. But this is just to kind of give us an idea and show you, that there's actually ranges in which the waxes are going to be relatively more effective than not. And so I love this photo. This is probably one of my most favorite photos that I've ever taken. When Turfway Park changed over back in 2020, we got to take a really good look at the synthetic racetrack. And so Jeff might be able to correct me if I'm wrong on this, but the track closed down at the end of March, beginning of April, and then that's kind of when the renovations began. And so the track wasn't actually truly fully worked in the hotter, warmer conditions. And what ended up happening is that we could see like, oh, on the top layers of the track, you can see that the wax is very black. The track is very black. We have very good coating of the material. But if you go down 3 to 4 inches, we actually can see the effects of the wax separating out just from the winter maintenance. It has this salt and pepper look to it. And it's only going to be until the temperature rises the material that it becomes more paste-like and it actually starts coating the materials again. And as you work it mechanically with the harrow, such as the cultivator, the Gallop Master, the power harrow. And one of my favorite things that I saw about this is that you can actually see that the material down there on the bottom there, that is the original Polytrack material that has never seen the sunlight. And I think that's just very interesting. You can see that, no degradation of the wax has occurred because the material's not touched or mixed. We don't have any of that carbon black material leaching out. But you can see that, there was no separation there, and that's just because the wax was never, or the track was never touched. But we do have temperatures affecting the track in such a way that you can visually see the differences going on. So I want to talk about one more thing, and that's this enthalpy in this crystallinity. And this is kind of like, I talked about steel versus aluminum. This is what's going to, really be one of those bigger differences is, how quickly will the wax heat up and cool off? And we can actually measure that relatively to one another. And so if we have this crystallinity, that means we kind of have like these semi-crystalline regions in the wax. Without getting into too much detail of that, it basically what it means is that it takes more energy, more heat to heat the wax up, or it can take less energy. So Turfway Park compared to WinStar 2017 and 2018, Turfway Park would have been able to absorb more energy before raising in temperature than WinStar did based on the enthalpies. And that enthalpy is going to be the area between that black line and the blue line. And that's how we're able to determine that through DSC. So what does that mean? Just for presentation purposes, let's just say that Turfway Park was this red line here. You can see that it is a lot smaller in these big temperature swings, and compared to what WinStar maybe would have been, with that blue line. Again, this is very inaccurate, but I just wanted to use this curve to show that, this crystallinity is going to be one of the things that affects these temperature swings of the track. And so if you can increase that enthalpy, the crystallinity of the track, you can reduce the temperature swings. So looking back at, the surface temperature versus the race times, we actually do have strong evidence that really does support this, and we can show that, yeah, you're probably going to have a difference with, the morning track versus an afternoon track. And so could we have tailored these thermal properties to reduce such an effect? The DSC provides evidence that, yeah, if we can sit here, we can measure, these changes in the heat conductivity of the surface. We can measure the thermal properties, and when these transitions in temperatures were going to occur, there is the possibility that you can actually, apply the method and use the method to determine, well, what temperature ranges are we going to be dealing with this wax, and should we use this wax maybe in Kentucky versus California versus New York, and we're able to provide insight on that. So once the wax is in, it's like sand. Once you put the sand in, you can't get the sand back out, at least not without removing part of the track or replacing it altogether. um and so people have looked at, the wax, the gel, the oil additions. That was briefly talked about, where Woodbine's adding wax and gel at the towards the end of the meet, just to help kind of with the winter. But one of the things that we're looking at is you're potentially adding more total wax to the surface. As a result of adding too much wax, you might start seeing the negative side effects of like a decline in drainage. You must add a lot of wax or a lot of gel oil to start actually making a difference. For reference, in 2017, Turfway Park did a wax addition, and that was about one tanker. So one tanker of the wax oil that was delivered was about 6,000 gallons. And for a mile-long track, that only changed the total wax content by about 0.3%. And that cost roughly, I believe, $40,000 to $50,000 for that addition. In the winter, to make it, keep the track looser and from separating out, I've heard of Silanol being used, which is like a silicone-based oil, and that's been added to help keep the track looser in colder conditions. But it could potentially be a band-aid solution, because when you add oils to a racetrack, there's actually the potential for the oils to actually strip the wax out of the racetrack, because it's dissolving the wax. And then when you have rain come through, it actually can kind of start washing that material out. And I have evidence supporting that. And then, of course, that causes the environmental concern of you losing material and everything through your drainage. And so what else can be done? in the case of Del Mar here, they found out that, yeah, they have to water the racetrack to keep the surface temperature down. By keeping the surface temperature down, you're able to keep the race times a little more consistent, or right where they were hoping or trying to keep them to be. And of course, could that have been avoided altogether by finding the right wax to match the thermal properties? Most likely. And that's one of the one of the powers of being able to use DSC and some of the other testing that has been identified to characterize these materials, is that we can actually test and confirm suppliers. If a supplier is going to come out to you and be like, I have this material, and we're going to add it to the track, we can actually show and see, well, is this material going to be right for you to add to the track, and is it actually going to potentially help address the problem, or potentially not do anything at all? So we are able to look at the thermal properties of these materials, we can identify them, and we can make decisions or help make data-driven decisions on whether or not you would like to move forward with a wax or not. So there's definitely more than meets the eye to when it comes to the synthetic racetracks. There's, we have a whole array of testing that we can do. The wax is complex. You're going to have these different fibers, these different chain lengths, and they're all going to affect how the material binds and what kind of mechanical properties we're going to have at different temperatures. We know that if we can decrease the thermal conductivity, make it more resistant to changes in temperature, you can reduce these temperature swings. We know that we can select waxes based on different temperature ranges, and we can measure and select these waxes based on data instead of the more of the touch and feel approach, and provide the evidence and proof that, this is the right material when the costs are so high. And of course, we know that there's a correlation to race times.